In this section, we're going to cover the exploratory data analysis and pre-processing stages. This section is going to focus on data cleansing tasks necessary to complete prior to the modeling section. We'll start this section by covering how to handle categorical data. Next, we're going to look at various approaches to imputing missing values and handling outliers before we move on to generating new informative features and finally selecting the most valuable features to model with. Here we are at the first video, where we'll discuss how to encode categorical data into a numerical state we can use for modeling. First, we'll look at the types of categorical data we might encounter. Next, we'll discuss challenges around factor level density we might encounter. And finally, we'll cover strategies and examples of encoding our categorical data. Categorical data can be defined as non-numeric data that indicates membership in some category. A very simple to grasp example is biological sex, male or female. Categorical data can be represented as a string type or by a set of integers. Note that there are select cases where numeric data may be considered categorical. It's important to distinguish between arbitrarily labeled groups and groups whose ordering has meaning. Non-ordinal categorical data has no natural ordering of factor levels. For instance, zip code or biological sex. It would not make sense to assert that 75001 is less than 77852, for instance, though it may be true in the numerical sense, because it's categorical. Ordinal data, though categorical in the sense that it's discrete, is generally still numeric and represents some implicit ordering. In the example presented, the education level integers correspond to credentials. In this case, it would make very natural sense to consider 10, which may represent a PhD level, to be higher than 6, a high school level. We treat ordinal data differently from other categorical data. It can typically be treated similarly to continuous data, save for imputation or transformation techniques. For instance, it would not make sense to impute a missing value with a mean or median, or to log transform the variable. If one or more of your categorical variables contains too many levels, there are several considerations you'll have to make. Too many levels means that when you encode your variable and expand your matrix, it will grow much wider, which will reduce model interpretability and increase model complexity at fit time. Second, you run the risk that levels will exist in the test set that do not exist in the train set. Many Scikit-Learn estimators or transformers will break down in this case. In the case of too many factor levels, it may make sense to create new ones by logically grouping levels together. In the example of zip codes shown, we could create country regions to cut down on factor level complexity. We will use one-hot encoding to encode our categorical data. This is similar to Boolean mask, indicating whether or not a value is present for categorical variable. Notice that by encoding, our matrix grows by as many columns as there are factor levels in the categorical variables. Of course, we dropped the original feature, so we lost one, but we still expanded it, and for a variable with many levels, this can cause the matrix to grow to a point of infeasibility. We've also encountered an interesting situation here, known as the dummy variable trap. This is when our dummy variables are 100% negatively correlated with one another. That's because male and female are mutually exclusive categories. We can rectify this by simply dropping one of the two new dummy variables. This applies for all dummy variables. By dropping one level, you can mitigate the dummy variable trap. Let's jump over to our heart disease notebook, where it's time to encode our categorical features. We'll be using a custom base class that extends base estimator and implements transformer mixin. It contains two functions: validate input, which ensures that the input is a pandas data frame, and validate columns, which ensures that the columns defined are present within the pandas data frame. Before we one-hot encode, it's important to grasp how the Scikit-Learn label encoder functions. The label encoder is a native class to the pre-processing submodule that transforms categorical data into ordinal data. The problem is, most times our categorical data is not ordinal. Therefore, we're going to build a class that leverages label encoders to create ordinal vectors, which we can then one-hot encode. There are several attributes we'll use in our encoding class. Columns is a list of the columns that should be dummied out. Sep is a character we'll use to separate the categorical feature name from its level name in the new header. Drop one level is a Boolean value that will drop one level per categorical feature to allow us to avoid the dummy trap. And temp nanrep is a string that will serve as a factor level for missing values in a feature. Let's move down here to the fit. First, we'll validate X as a data frame and that the columns exist within X. Notice we call the validate input function and then validate columns function. Then we're going to fit label encoders for each user-defined column. For each column, we'll want to use a list comprehension to replace null values with our missing level string we defined in the constructor. That's what's happening right here. Next, we'll get the unique values from the vector and ensure that temp nan string exists. It's important it does in case our test data is missing any values in this feature, even though it may not be in the training set. Next, we'll fit a label encoder on the factor levels in this vector and map it back to our dictionary keyed by the column name. Since we have a copy of the input data frame, we'll go ahead and transform the existing column to the label encoded one. This is important since we still have to fit our one-hot encoder after this stage. After all defined columns have been transformed and have fit their label encoders, we'll fit a single Scikit-Learn one-hot encoder. Once the encoder has been fit, our custom transformer has been fit and we can return self. The transform stage behaves a lot like the last half of the fit stage. As always with an estimator, we're going to check that we fit it already. Next, we're going to validate our input and create a copy. Now for each column we've defined, we want to recreate via list comprehension the values that will be transformed by the corresponding label encoder and set that in the data frame. At this point, we deviate a bit. Since label encoders store their labels alphabetically, we know that the input-output to the one-hot encoder will emerge in alphabetical order. But since it's a NumPy array, it won't have the names attached. So let's grab the class names in order here before moving on to the next column. If we've decided to drop one level, and if there are enough levels in this categorical variable to do so, here's where we'll capture the name of the column we'll drop later. We arbitrarily choose the last factor level. Now we'll use the one-hot encoder we fit before to transform the label encoded columns, turn the NumPy array back into a data frame, drop the defined factor levels out, and concatenate back onto the original data frame, finally returning the transformed data frame. Here we can take a look at what the transformed output looks like. You can see that we have some categorical variables here. Rest ECG, one of the levels was normal, and here you can see we get dummy variables 0, 1, where that's the case. You can also see an example here where we have one of our missing levels. Since there are none missing in the training data, they're all 0, but if there are any missing in the test data, this way we won't error out.